told her about that next.
What did she not say?
I said, you may not say, let me come.
Work. Today we are starting with internal energy. But where did we even stop last time? Preparing. Okay. Okay. Let me share my screen so we can start. And then let me share the YouTube link as well. Okay. So today, let's start with internal energy. Some of the concepts will be discussed more in details as we go along. So we started talking about thermodynamics, energy, conserved energy cannot be created, and then we defined the system and surroundings. We also described work and heat. Those are the ways that you can change the internal energy of the system. Of the energy of the system. The internal, did we do this last time? I don't think so. The internal energy of the system okay, just to be sure. So the internal energy of a system is the energy due to the spatial arrangement of the system. And again, we can have the total and the kinetic and the potential energy components. So it's a sum of all kinetic energy. Kinetic energy is due to motion, the different motions that we have within the system. There are rotations, translations, vibrations. So translation is motion in straight line. A rotational motion, that's rotation, that's about a point. You have a molecule that is moving about a point, or maybe a diatomic molecule moving about its center of mass. That's an atom. Vibration is an oscillatory motion, movement back and forth from one equilibrium line. Potential energy is due to the statics present, the electrical charge present in atoms within the molecule. The internal energy, some facts about it is that it is a state function. So internal energy, U, given the symbol U, tells you the capacity of that particular system to do work, whether it's pushing whether it's transferring energy in form of pushing a distance or in form of heat. The absolute value, that's absolute U, is always difficult to obtain. However, because more often than not, we are interested in a change from an initial point to a standard to another point. So U of A, U of B. The change in internal energy associated with this system is of more interest, which is the final minus the initial. So the beautiful thing is that internal energy is a state function. And when you say state function, it means that you can simply put it as the final minus the initial. So state function minus initial, you can easily calculate it as that. So it depends only on the present state of the system and not on the path in which you arrive at that. If you are looking at it for a reaction, it's the final, which is the product. A reaction is converting reaction, that means converting reactants to products. So the final reaction is that the thing is that because this, again, like I said, they are difficult to measure, we can measure the change in internal energy by understanding how much work is done on the system or how much heat is supplied to the system, depending on the condition of reaction. Condition of reaction. So that it is a state function, it can be measured. This change can be measured by other means. The first law of thermodynamics the U in itself is a function of the amount of particles present in the system. And because of that, we call it an extensive property. We call it an extensive property because of that characteristics. So once you change the amount, once you change the amount of particles, U also changes. You can change the internal energy by work or heat. It's given the symbol W, and heat is given the symbol Q. The first law of thermodynamics is related to the law of the conservation of energy. We already said, so energy cannot be created nor destroyed. However, we can convert it from one form to another. Mathematically, it is given as that for a closed system, emphasis on the word closed system. Remember, we have isolated system, we have a closed system, and we have an open system. For a closed system, the change in internal energy is a sum of the heat flow through the barrier and the work done by the system through the barrier. It's a sum. So if the heat flows out, then it goes out of the system. Then the internal energy is reduced. If heat flows into the system, the internal energy is increased. Same thing as work. If you do work on the system, internal energy is increased. If work is done by the system, internal energy is decreased. So in this picture, internal energy is given the symbol E, but usually we're using, in our case, we are using the symbol U. Initial state, final state. Energy is gained if you're going up. Energy is reduced if you're going down. The sign convention used in thermodynamics. So you have your system. If you have your system, so delta U, that's you transfer heat to the system. That's what I just described just now. If you transfer heat to the system, internal energy is increased. If the system transfers heat, internal energy is reduced. So once the system loses heat, we say it's an exothermic process. So here, U decreases. With transfer in, U increases. Same thing, if work is positive, U, internal energy, increases. And if work is transferred out, U decreases. That is the general sign convention. Let's work an example. An example is calculate the internal energy U for a system undergoing an endothermic process. So once you see endothermic process, you know that it is supplied to the system. So that's positive Q, in which 15.6 kilojoules of it flows, and where 1.4 kilojoules of work is done on the system. So from our question, we know from the first law of thermodynamics, so here we are going to assume that we are dealing with a closed system. From the first law, we know that the delta U is the sum of Q plus W. From the question, Q is positive because it's an endothermic process. Also, W is positive because work is done on the system. If we had said that work is done by the system, then work would have been negative. So the delta U now would be positive Q plus positive W. That gives us 15.6 plus 1.4. That gives us 17.0 kilojoules. Another example, a sample of an ideal gas in a cylinder of an engine is compressed from 400 ml to, we said compressed, 600 ml against a constant pressure of 8.0 atmosphere. At the same time, 1.40 joules of energy is transferred from the gas to the surroundings at E. So Q will be what? Q will be negative because we are saying it's transferred to the surroundings from the system. So minus 140 joules. What is the total internal energy, change in internal energy of the gas in joules? Sorry, joules. So we convert our given unit to standard units. So delta U from first law for a closed system, an ideal gas in a cylinder. So that's a closed system that we have, is compressed. Closed system. Somebody still has his mic on. Please mute it. I can't keep going between Zoom.
That's the thing. I don't even know.
I can't keep going between Zoom and the presentation. It's going to delay us. So, like I said, system transfers heat. So Q is minus 140. work is done by the system because it's compressed. We are going to get our work being positive. Recall that this definition is based on saying that the standard definition, W, is work done by the system. So if you're saying work done by the system, you always define it mathematically with this expression. It's your delta V that will help determine in the end whether you're going to get a positive or a negative. And delta V is always V final minus V initial. So our V final, that's the one that we have designated as V2 minus V1. So V1 is 400, that's the meter cube there. And V2 also is milliliter, so that's why it's that small. V2 is 60 milliliter. So you have it converted to SI unit. Pressure, we also convert it to the SI unit. The V is not supposed to be there. So what do we get in the end? Minus of the sign here, pressure times final volume minus initial volume. What you would also note here is that our final volume is smaller than the initial volume, and it makes sense because it's a compression work, and when you're compressing, you should get the work is done on the system. So if you do all your calculation, you would arrive at a positive 275.604 joules. So that's pressure times the change in volume. So we go back to our equation for a closed system to calculate the delta U because that's what the question requires. And then you arrive at minus 140 plus 275. So while work is being done on the system, it is losing it. Well, we still have a net increase in internal energy. Okay. I want to believe no question. Comment. Let me see comment.
Not the question.
Please hurry up so that I will move on. We started the class late.
Master, like pressure times volume equals to work done, right?
Pressure times change in volume, not pressure times volume.
Equals
Pressure times change in volume. That's
equals
symbol
to work done.
Yes.
Okay.
Hurry up, hurry up. You have 2 more seconds. Okay, so let's move on to the other concepts of thermodynamics, of thermochemistry.
I have a question.
Hurry up, hurry up. Or you said your
Is
question
there,
on half books.
is there any situation whereby the internal energy of the system is reduced or negative instead of the regular positive?
Of course. See, you know all these things.
When the
Like
system
in
is
nature,
expanding,
listen now, like in nature, if you go out and make heap for yam from morning till night, what do you think would happen? You're working, you're doing work. The internal
Yes.
energy of that your system, what will happen to it? It will reduce. And that's why when you get back home, you want to eat to increase the system, internal energy again, to increase the capacity to do work. Same
Okay.
thing, people that are running up and down because they want to lose what? They want to lose calorie. That's the in thing nowadays. You want to lose calorie. Lose. Is it not to reduce the internal energy? Yeah, that's
Yes,
what
ma'am.
it is. So always try to look at it from what you see every day. When you're cooking a food, you're increasing the internal energy of the food so that it can increase your own internal energy in the long run. When you're studying, you are reducing your internal energy because you are trying to grasp something and you use energy to do that. So it depends on the net process. You either balance it out or you lose or you gain. That's it. It depends on process. In a human body, there are several processes going on at a point in time. Some require energy, some produce energy. So moving on, I'm not sure I have time for another.
Ma, please go.
Oh yeah. I've heard
Yeah, ma, I
this.
want to ask about the work done. The work done in the
What about
system.
it? This one
The
that we
work
just did.
done.
Okay.
Yes.
Ask
So why is the work
now.
done and why is the work done negative? Like why is it negative? Pressure times change in volume. Can it be positive?
Somebody just asked something similar.
No, it
And
was
the
asking
one
about
that we
internal
just
energy.
wait, no, so I said something similar. Don't try to be smart with me. The work done that we calculated here is positive, isn't it? The work
Yes,
done that we
ma'am.
calculated in the previous class, Daniel, was negative. It
Yes.
depends on the condition that you are dealing with. If it is an expansion work, the work done will be negative. If it is expansion,
Okay,
the work
ma'am.
done will be negative. That's the thing. So there's no saying that this is always this, that is always that. The nature that we are trying to understand. This is something that I also want all of you to get. All this that we are trying to learn is in a bit to understand more what goes on in our environment. And our environment is the planet. And it happens every day in everything that you do. The way I'm talking now, I am doing work, which means I am losing energy. That's the thing. You are learning, you're using energy to learn, to grasp what I'm saying. You're doing work. You will replenish, so the energy can be replenished in another way. So you can have that a car that you want to use to drive from one place, you add fuel to it. So you are increasing its capacity by adding fuel to it. So it depends on what you can't just look at something and say, is it always this? Is it? No, that nothing is always that. The only thing constant is food that we are still trying to find out. All right.
Thank you very much.
Enthalpy. Now let's look at the concept of enthalpy. So we have looked at work, we have looked at heat, and then we have looked at internal energy. Enthalpy is the measure of the total heat content of the system. And U is internal energy of the system as a result of the things that are present in the system, the molecular components that are present in the system. So enthalpy goes a step ahead. So those internal components, they have their own internal pressure and they occupy a certain volume. So that is the enthalpy of that system, the total heat content in terms of energy at constant pressure. So you will say that it includes energy, internal energy, and the pressure required to create volume that it occupies. In a similar way, it is often also difficult to measure. But the beautiful thing is that it is a state function, meaning that it depends only on the state of the system. So when we say state function, let me do that quickly now. There are some things that are called state function, and there are some things that are called path or process function. A state function depends only on the state of the system. It depends on what you have present in that system currently. It does not depend on how the system was achieved. A path or process function depends on how the state was achieved. An example, a common one that you can easily relate with, and then we'll come back to chemistry, when you talk about distance versus displacement. If you want to go from here to, say for example, let's say you are in Yaba and you want to go from Yaba to the airport, so that you want to fly and travel out. You can go through different routes. Those different routes are distances that they would have a certain distance that you covered. And that distance will depend on the routes that you take. So you say that distance is a process function. On the other hand, the net displacement is between Yaba and the airport. It does not matter how you get there. All it needs that your endpoint is the endpoint. Okay, so the displacement is a state function. So when we state function, so your displacement is position airport minus position Yaba. Simple. That is it. Your distance is, did you go through Oshodi or did you go through Maryland? That is the one that you now calculate or did you go through Mushi to connect this place down, to connect Matu, to finally connect Oshodi. So that's the distance that it depends on how you achieved, how you arrived at. So those are the ones that we call part and process function. The ones that we always deal with, the work done and the heat supplied, are process functions. Then the ones that we're talking about, so I've given an example of a state function before, that is the internal energy. The enthalpy that I've just described to you now is another state function. And that is why the change in internal energy, change in internal enthalpy is simply the change in the final state minus, the value of the final state minus the value of the initial state. Again, these absolute values are always difficult to measure, but there are other things like work and heat that can help us calculate the that are related to the change. For example, we were talking about the displacement the other time. Once you know the latitude and longitude of airports, the latitude and longitude of Yaba, you can talk about the displacement. Now, how you got there is another totally different ballgame. So, usually, the heat of a reaction, the change in enthalpy of a reaction is equal to the heat of that reaction. That's the heat flow. Heat flow, that's Q, heat flow Q at constant pressure. The enthalpy of a reaction is something that is of interest in everything. A reaction takes place every day, everywhere. In food, in cooking, in your body system, in the biology lab, in the chemistry lab, so reaction takes place every time. So we are interested in the enthalpy of a reaction. The enthalpy of a reaction is the enthalpy of the product minus the enthalpy of the reactants, because you can have several things in the product, several reactants. So we have sum of all the enthalpies of the products minus sum of all the reactants of. So the equation that we wrote here last time is H final minus H initial. So our final represents the products, initial represents the reactants. If H product is greater than reactant, that means this equation will be positive. We say that the reaction is endothermic. For such reactions, you need to supply it to the reactants to get a product. An example is when you're warming ice, you need to supply heat to it. If on the other hand, the product has lower energy, so those kind of reactions that people are always trying to create more energy. So it means that your reaction gives off heat. So this is an exothermic reaction profile. And this is an endothermic reaction profile. So you see, the product, the energy of the product is higher than the energy of the reactant. So for this kind of reaction to take place, you need to add heat to it. Something to note here is that, I've said reactants plus heat, and here I put products plus heat. That's because in a chemical equation, the chemical equation that is used to represent what's going on in a chemical process, you hardly use the symbol minus. One thing to note here is that whether you are adding it or you are not adding it, there's still a barrier that the reactants must overcome. So that's not our concern. It's the concern of the field of chemical kinetics. We are not talking about that in this situation. Thermochemical equations often involve the amount of heat required for a reaction or the amount of heat given off. So when you have a balanced chemical equation that shows the associated enthalpy change delta H, you call such equations a thermochemical equation. So this is a thermochemical equation. Now, if it is only this, it's just a regular equation. Now, I said something in the previous slide. This equation, this thermochemical equation that we have here, it shows that delta H is negative, meaning that heat is given off or the reaction is exothermic. We can write this reaction in this form. So the reactants combine to give products and they also give off energy. And this is the amount of energy given off. So this is actually our standard thermochemical equation, but both of them are allowed. Another example, you have water so this is liquid water being converted to gas. So that's water being converted to what we call steam. The enthalpy of reaction is positive, meaning that we are dealing with an endothermic reaction, or that for the reaction to take place, it has to be absorbed. So in this case, the alternative way to write this expression or this chemical equation, your reactants require it to get the product. Note that I did not write the heat on this side to say minus 40.66 because that is wrong. You don't use the negative sign. You only use, please mute your mic. You only use the positive sign for the reaction. Okay, wherever it is. Thank you. So what do you think for this expression here? If we want to write it, is the energy going to the positive side, to the reactant side, or to the product side?
Going to the product side.
Product side.
To the reactant side.
Product side.
Product side.
Okay, so final answer. Mute. So it's going to the product side because heat is given off. So same characteristics of H that I described for internal energy the other time is they are state functions and they are extensive. Extensive means that they depend a function of the amount of substance present in the system, where n represents amount or number of moles. The implication of these two things, being a state function and being an extensive property, the implication is, the first one is that if you reverse a reaction, the delta H for the reaction changes. For example, this reaction H2O, that's liquid water, going to the gaseous water, which is steam. We already said this is the amount of energy required for that reaction. It is endothermic. If you reverse the equation, that is H2O gas going to H2O liquid, that's condensation. It is now that it is given off. So once the change in reaction is equal in magnitude, the change in enthalpy of a reaction is equal in magnitude but opposite in sign to the enthalpy of the change in reverse reaction. Now, this one is a consequence of the fact that it is a state function. It does not matter how you got it. Then, for the second one being extensive, is the second one being extensive. If you have conversion, this is a carbon monoxide going to dissociating back to graphite and oxygen. The delta H for that reaction is 110. So of course, like in the first one, if I go back, half O2 plus graphite to CO2, delta H will now be negative 110 equals negative 110. Okay, but that's not where we're doing. Extensive, if I now increase, this is 1 mole of carbon dioxide, carbon monoxide, carbon 2 oxide going to graphite. So if I increase it 2 moles to give 2 moles of graphite and 1 mole of oxygen, the delta H of that reaction will now be 2 times that reaction because I have multiplied it by 2. I multiplied it by 2. So the change in enthalpy is multiplied by any factor that multiplies the reaction. That is a fact because they are extensive properties. Extensive properties depend on amount of substance present in the system. Let's work an example. Now, how much heat is released when 4.50 grams of methane gas with that formula CH4 is burned in a constant pressure system? A constant pressure, when you're dealing with constant pressure, you're dealing mostly with delta H. We wrote it the other time. Delta H is the heat given off at constant pressure. So the subscript here.
Yes, ma'am.
Yes. The subscript is talking about constant pressure. So we're given that, I'm writing this equation in a bigger way, given that CH4 plus 2O2 to give CO2. So this is an example of a combustion reaction. Combustion reaction means that whatever your substance, you are reacting it with oxygen, or more appropriately, you are burning it in oxygen. If you bring oxygen close to anything, it burns it. Delta H for the reaction is 8.090 kilojoules per mole. More often than not, delta H is for standard in the table of values are reported per mole. So we know that 1 mole gives 890 kilojoules of energy. The question is how much it is given off by 4 grams. Luckily, we also know that there's a relationship between mass and number of moles. A mass of a substance and number of moles, there's a relationship between that. So all we need to do is to know that how many moles do you have in 4.5 grams of methane. So this is the relationship, the number of moles, N is number of moles. The number of moles is equal to mass divided by molar mass. What is the molar mass? The mass is 4.5 grams. Molar mass is obtained by looking at the formula. The formula is 1 part carbon, 4 parts hydrogen. So that would be 4 times mass of hydrogen plus mass of carbon. Mass of hydrogen is 1.008, approximating to 1. And mass of carbon is, so we have that in gram per mole. If you slot that into this equation of number of moles, we know that the number of moles that we have is 0.82281. So if we have 0.281 moles, if you have sorry, I'm just looking at the comments on so that I know if I am to slow down or not. So if you have 0.281 and we know that 1 mole gives us 890, we can easily use a cross multiplication, and then we arrive at 0.281 giving off 250 kilojoules of moles of kilojoules of energy. So that is our answer. Let me see if I have time for another slide, because I have another class by 10, so that I don't break down. This next example is similar. Any confusion? Question? 5,
Excuse me,
4,
excuse me. Why
3.
we're given two?
Continue now.
Okay, sorry. If we're given 2 moles of that methane initially, we'll be comparing 2 moles of methane to the amount of heat that is in the system before. Yeah, let me talk finish now.
So
Yeah, so we'll be
repeat what
comparing
you said. If you are given 2 moles
yes of
initially.
methane, yes. Or maybe we might have to balance the equation at some point. So we now
It
have to
is
compare the 2
exactly
moles.
whether you like it or not. If you are given a question, how much of it is, if you are not given the equation, you need to, so that's why I went ahead to tell you this is a combustion reaction. If it says that in the combustion reaction of methane, you do have to balance that equation. Equation needs to be balanced. Okay,
Okay,
so
ma.
now move to your question.
Okay, ma. So as when we now balance it, for example, so if I get something like 2 moles of methane, giving us minus 890 kilojoules of heat, so we have to
So
compare the 2 moles to. So we're
yes,
doing comparison
no,
method.
so please, one thing is important. It's part of the things that I was saying. The delta H is given as 890 kilojoules per mole. So if it's given as kilojoules per mole, that's going to probably be given as 1.
Okay, yeah.
If I just write an equation, I do not write per mole. You need to look at it critically.
Okay.
So you get it.
Yes, ma. Yes, ma.
That takes us back to life examples. Anytime you get to a situation, you don't just rush into it, you critically assess it before you make whatever you want to make. The other person that wants to ask a question, please, what is it?
My
No
question
question.
is why is
Hurry
the
up, hurry up. How do you?
negative? My question is why is the delta H negative?
That is the given in the question. Did you
Okay,
not see
ma'am.
the question?
It's because the reaction is exothermic now. Many times
Thank you
repeated.
very much. It is given in the question. So this one is a simple one. When 2 moles of, so it's related to what? When 2 moles of hydrogen, please
Use
mute.
that one.
Yeah, mute your mic.
Abeg, mute your mic, abeg.
When 2 moles of hydrogen and 1 mole of oxygen react to give liquid water, see, 50 kilojoules of heat is given off. So what is for these 2 reactions? So if you look at the second reaction, so look at your equation, 2H2 of gas plus O2. If we don't write anything here, it means that we're looking at 1 going to 2H2O. Delta H is liquid minus 572 kilojoules. Please note the emphasis on the states of your substance: gas, liquid, solid, aqueous. When you're dealing with thermodynamics and thermochemistry, all those things are important, because you can write H2O. It can be liquid, it can be solid, it can be gas. So if you compare this reaction to the first one, you will know that it has been divided by 2. That reaction is divided by 2 or multiplied by half. So your delta H will be multiplied by half. In the second one, it is a reverse. Let's compare this to that. So that's supposed to be liquid, sorry, liquid. So it is a reverse of that reaction, and our delta H will be 572. So that we can move faster. Huh?
Ma, can you come again? Can you repeat what
Which
you
one?
said earlier?
Which one? Which one? Which
That's
one?
law of extensivity now.
I said
Yeah,
the one that's going to be multiplied by 1/2.
look at this. Read this expression, please. Compare this reaction to that one. You would realize that it has been divided by 2, or if you want to look at it, so therefore it's multiplied by R. So the delta H will be multiplied by R. Yes, that's the thing. It's because it is an extensive property. According to the person that spoke, law of extensivity. I have a class now, so I'm going to stop here. We're going to start talking about calorimetry. We still have a lot to cover. There's this, I don't know what text has been told, you have been told, but there's this textbook, Chemistry, the Central Science. It will contain all topics that myself and other lecturers are going to be teaching you. So please, I'm sure it's available in bookshops, and I also know that if you go online, you can get a PDF copy. Because I'm going to move much, much faster on Monday. Thank you.
Facebook.
Huh? I've just wrote it. Central Science.
Chemistry Central Science, guy.
One of the authors is Brown. There are several authors. There are about 7 authors, but the first author that they usually write, his name is Brown. Okay. So thank you.
Where's the slide? Can you send the slide?
Okay, yes. Please, somebody should remind me. I'm going into another class now, so that's not what I'm going to do.